In this video, we will be talking about degrees, radians, conversion factors, and the angular and linear velocity. The conversion factors will be involved with radians and degrees, as well as your inward problems involving angular and linear velocity. It's not all the time that given specific units, that's going to be the same unit for the final answer. Some word problems can ask you to, some problems will require you to convert the current units you have into a different set of units. For instance, feet per inches to miles per hour. And that's where conversion factors come into picture. So let's start with degrees and radians and their corresponding conversion factors. We basically have two formulas here. To convert from radians to degrees, we multiply the current quantity by 180 degrees over pi. That's from radians to degrees. When it comes to converting from degrees to radians, we multiply the current quantity with pi over 180 degrees. Let me give you a tip on how to memorize them. For the letter blue, highlight from radians to degrees. For instance, we have 12 radians or 12 theta radians. Usually, radian quantities have theta beside the constant number. In this sense, you'll always think that from radians to degrees, radians, remember that the numerator will always be 180 degrees and the denominator will be pi. So in this case, from radians to degrees, radians, just remember that it's 180 degrees to degrees. I hope that helps. As to how I interpret it, it's really been helpful. Even if I don't actually memorize them, whenever I say radians to degrees, I remember radians, numerator is 180 degrees, and yeah. But another way to memorize the formula for converting from radians to degrees, given you have this quantity, 12 pi radians, just remember that we have to eliminate pi. So in this case, we eliminate pi and yeah, magic happens. 12 rad and times 180, or in other words, 12 times 180 degrees. So yeah, let's try letter A, practice question. So we have to convert 75 degrees to radians. So from degrees to radians, we have to identify the current unit of the value, which is 75 is in degrees. So we convert it to radians, so deg to rad. What's the formula? It's this one. By the way, I might have not introduced this formula properly, but it's just the opposite of formula radians for radians to degrees. Whenever you hear an initial quantity of, for instance, 70 degrees, it has the unit degrees. Convert it to radians, just always remember that pi will always be in the numerator with the value that you will be multiplying it with. So this is the solution. And yeah, just go ahead, place this in your scientific calculator. I'm already assuming that your teacher allows scientific calculator use in your exam, so make the most of that opportunity. Okay, let's go back to the actual question. 75 degrees to radians. So let's just put 75 degrees over 1. Then what's our formula for degrees to radians? It's pi over 180 degrees. So let's apply it to our current solution. We get something like this. Place these values in the scientific calculator. Our answer is 5 over 12 pi. This is the final answer. So this is 75 degrees in radians form. So for letter B, we convert pi over 24 to degrees. So as you can see here, the value, the fraction itself has pi. So we're starting to assume that it's radians. It's a quantity in radians, and we're supposed to convert it to degrees. What's the formula of converting from radians to degrees? It is 180 degrees over pi. That's our formula. We multiply it with the current value. So pi over 24 times 180 degrees over pi. Cancel these two. Cancel pi, and we get 180 degrees over 24, or just basically 180 over 24. And if we simplify that in simpler terms, we get 15 over 2. This could be our final answer, or we could also put its decimal form, 7.5. So I'm not sure what your teacher requires for your answer to be in what kind of form, whether fraction or decimal, but I've already given you the two possible answers, and if your teacher prefers that you put your final answers in fraction form, then so be it. If your teacher prefers it in decimal form, then you also have the decimal answer here. Alright, let's move on to the other formulas. We've already tackled radians to degrees and degrees to radians formulas. So for radians, basically the formula stated here, it's already assuming that theta is always by default expressed in radians, not degrees. So you'll have to take note of that. Always by default expressed in radians. You have to always remember that theta is in radians, since trust me, if you think that by default theta is in degrees, that's already automatically wrong. It will screw up your solutions no matter how much comprehension you put into other details that's stated in the word problem itself. You do have to acknowledge that theta is in radians again. You don't want to repeat the mistakes that I had in back in the day, back when I used to answer problems involving radians. Anyways, next formula is for the arc length. It's basically S equal to R times theta. Of course, theta, again, is always expressed in radians. That's by default. For the next formula, I won't be discussing too much on the formulas. I'll be telling more about it when we actually apply it in real world problems later, and for the next videos possibly. For area of the sector, A is equal to 1 over 2 times R raised to 2 times theta, such that R is, in other words, radius. If you could recall this definition, it's basically the diameter divided by 2, but you won't really have to think about that. Just remember that R is radius, not radians, just radius. You might confuse R with two terms that are involved in this lesson. Of course, theta is still expressed in radians by default. There's another formula that will come in handy. This was never introduced by in our class, in our actual school, but then I discovered it from another wise teacher from the internet. A, or area, is equal to theta over 360. I'm assuming this is in degrees, but we don't have to expound on that specific detail. Theta over 360 degrees times theta times R raised to 2. I hope I'm not wrong with this formula. But this isn't exactly stated in classes, but then whenever you're going to find, you're tasked to find the area of a sector, this is the formula that you use. The A is equal to 1/2 times radius raised to 2 theta. For whenever you want to find, or you're required to find either radius or theta, given that you have a specific area, or maybe it could possibly be modified, like assume that the area is doubled, or assume that the area is added with 50% of its initial value. um, just know that for this formula, this will come in handy. I realized that when you use this formula in finding the radius and theta, it's not exactly as useful. Actually, it's not useful at all. You'll find a different answer for some reason. But anyways, I'm telling you right now that this is the formula that you use to find a missing radius or a missing theta value given area. Of course, consequently, here for the area of a sector formula, this one that I'm pinpointing right now, it is already assumed that you have the radius value and the theta value. All you have to do is to find the area. Basic algebraic uh, solving. Anyways, so let's apply. Let's have a few practice questions. Using the formula for arc length. So this is one problem about it. So given a circle, the radius is 10 centimeters. So we know the unit is 10 centimeters. The arc length is missing. So that's S, in other words. As you can see here, S. And subtended by the angle of 3.5 radians. You might be wondering why the given is in broken English. I already simplified the problem for you. I wrote it in a more simpler way. So all you have to remember is that radius is 10 centimeters while the angle is 3.5 radians, or the theta is 3.5 rad. So let's rewrite them again to make sure. You don't have to do this, but if you're not sure, if you want to be careful, extra careful, then feel free to do so. Angle, let's just say theta, is 3.5 rad. So again, as stated earlier, let's recall that theta is always expressed in radians. So we don't have to convert values to a different unit since they're all acceptable. Regardless of the unit of radius, I think everything is acceptable. Meter, centimeter, anything in the metric scale, I think it's acceptable. In the meter scale, yeah. Anyways, so radius is 10 centimeter, so 10 times theta, which is 3.5 rad, S, so 10 times 3.5 is 35. Our unit for the S, or the arc length, is always the same as its radius, which is in centimeter. So this is the final answer. Okay, using the formula for area of sector, or area of the sector, so given we have the theta value and the radius, these are the two things that we need whenever we want to find the area of a sector. So again, let's recall that the area of a sector is 1/2 times radius raised to 2 times theta. So area is equal to 1/2 times our radius is 72 feet raised to 2, then our theta is 3 pi over 4. Oh, I'm sorry, I'm not supposed to use black pen for writings that aren't formulas. It's a basic school of thought for me. I trained myself to think that way whenever I write with colored pens. Feel free to adapt to how I also write. Anyways, in the calculator, if you put these values, we get 1,944 pi square feet. Of course, this is a basic principle in geometry. If we want to find the area of something, its unit will always be the measurement, which is initially feet. As stated here in the radius, it's obviously feet. You always put squared. So yeah, this is the final answer. Let's move on for further practice questions. So Quito is approximately 78 degrees west longitude, and while Macapa is at 51 degrees west longitude also. And the radius is 3,960 miles. So the question is, how far apart are the two cities, Quito and Macapa? So first thing we need to do, so we know the value of radius, but we don't know the exact value of theta. But we were given a clue. 78 degrees and 51 degrees. Please don't expect me to say why the solution is actually how it is. I just know that this is how you do it. So the greater degree, that's your initial value, then you minus the smaller value. So 78 degrees minus 51 degrees. Theta is equal to, please use your calculator or just compute it manually. It's 27 degrees. So this is our theta. We can now solve them. So assemble. Radius is 3,960 miles. Then we multiply it with 27 degrees. So hang on. Before that, this is a mistake that I finally made again. So as stated earlier, theta is expressed in radians. As seen here, it's not expressed in radians. Theta is expressed in degrees. So what's the value of theta in radians? Let's see. So from 27 degrees, multiply it. 27 degrees to radians, it's theta over 180 degrees. So put this in the scientific calculator and we get 3 over 20 theta rad or radians. With that in mind, so S is equal to radius, which is 3,960 miles, times theta, which is 3 over 20 theta rad. Our answer for S is equal to 594 theta miles apart. Or hang on, let's modify our answer. It's not always that. I'm not sure how your school wants you to write as your final answer. If you don't have to like simplify theta, you could just write 594 theta or any number with theta. But it's a lot safer to write them both answers that are the same. So 594 theta is, in other words, 1866. So yeah, this is the complete reference. Alright, so I'm assuming this is correct already. I have the answer key here right now. So yeah. Next, let's move on to angular and linear velocity. We are introduced with two formulas. For angular velocity, it's W. So angular velocity is W, then it's equal to theta over time. There you go. While for linear velocity, it's basically V is equal to RW. You don't have to note about this one. You just think about V being equal to RW. The way I'm able to remember the formula for linear velocity is just imagine, just write V and as you can see here, W looks like a fist. I don't know, my mind looks awkward, but then this image resembles me of like a kung fu fight, a kung fu punch. So that makes me remember this formula a little easier. But even so, you could feel free to find your own way to memorize it more easily, or to remember it, recognize it. Anyways, for number one, let's apply what we have. By the way, before we start the practice questions, you have to know that 1 revolution is equal to 2 pi radians. Or in other words, revolution, by the way, can also be called in certain word problems as rotation. So you might want to note that it took me quite a while to realize that rotation is revolution in the context of this lesson. But then I think we all know that rotation and revolution, they're different in the context of science, specifically in our knowledge about the solar system. Rotation is very different from revolution. Alright, let's move on to number 1. So wheels racing on a bike. So the radius is 13 inches. The velocity, or how fast the bikes race, or how fast the wheels go, is equivalent in blank miles per hour. Wheels turn at 300 revs per minute. So at first the problem looks intimidating, but then it will be a little easier once we dive in. So radius, I'm sorry, I just have the habit of rewriting the given. It's been a habit, even though it's redundant, and I just want to make sure. Feel free to solve it your way if you don't think that mine is efficient enough. I know it's quite boring. Anyways, radius is 13 inches. First, we have to find, in order to find the linear velocity, we have to go through the solving for angular velocity. So, find angular velocity first. So, angular velocity is W equal to theta over time. In that sense, our theta is missing. But we could find what theta is with the statement, with the given 300 revs per minute, or revolutions per minute. So with angular velocity, just write 300, then times revolution. Then below, it's 1 minute, since it's stated here in the given per minute. So that is our time. And let's apply this formula. 1 revolution is 2 pi radians. So 300 times 2 pi over 1 minute. Basically, we get 600 pi over 1 minute. And this is our linear velocity. Hang on. Yeah, this is our linear velocity, but no, this is our angular velocity. I'm so sorry. This is our angular. But this isn't our final answer yet. Now that we know angular velocity, let's solve for linear. I might ask earlier why we have to find angular velocity first. The reason is we don't know what W is in the formula of linear velocity. W stands for the angular velocity. So I hope that clarifies your possible question. So V is equal to, what's our radius? 13 inches. Then the W, or the angular velocity, is 600 pi radians. By the way, it's best if you put rad after every numerator in the angular velocity. It's more appropriate if you put the unit of a quantity. So just for the radius, I happen to later on realize that it's best if given any quantity of radius, the denominator will always be 1 rad. So 3 inches per 1 rad. Any value of radius per 1 rad. I cannot justify that claim, but then it did work for more solutions that I answered later on. It no longer led me to more complicated solutions that didn't lead to actual answers. So yeah. Anyways, so the question doesn't exactly require you to convert your initial units to another specific set of units. So I think this one is um, good enough. Wait, no. Um, your the question requires you to have your answer in a specific set of units called miles per hour. Initially, ours is inches per minute. You can see it here. Assuming that we've already cancelled rad, so inches per minute. So we have to turn that into miles per hour. How? So here is where this is the lesson on conversion factors involving linear and angular velocity. So from inches, we know that. Sorry, I just want to place it here. Place this here. So convert in minutes to hours. We have minutes here. We want it to be in hours, and for the measurement itself, that's in meters. Um, we convert inches to miles. So 1 mile is 5,280 times 12 inches. Um, you could I think you're required to memorize these values. So if I were you, start memorizing it now. Um, try finding ways to memorize it. Uh, anyways, so we know that 1 hour is 60 minutes. So here we put 60 minutes at the numerator and 1 hour at our denominator. How did I write? Why not, you might ask, why not place 1 hour here in the numerator and 60 minutes at the denominator? Well, our objective is to cancel out the initial units and bring in the new units. So here we have hour. So we have to remove inches now. By the way, I want to extend what's stated here. So 1 mile is equal to 5,280 times 12. Or in other words, this is 6,300, I'm sorry, 63360. 63,360 inches. So if you want to memorize, like associate 1 mile in inches, just keep on remembering that 1 mile is equal to 63360 IN. So that's how I memorized how much 1 mile is in inches. So 63360 inches. Then above we have 1 mile. With this in mind, we cancel the inches and we get mile and hour. Those are the new units. So we just have to place all these raw values on our scientific calculator, and our answer would be, hang on, for a while, please bear with me. I'm starting to assume that the answer is 23.2 miles per hour. So there. This is the linear velocity. Let's move on to the next question. Actually, this is already the exercises, the chapter exercises for this lesson. This entire lesson is primarily based, by the way, I do have to say this. This lesson is primarily based on a book composed or authored by Mr. John Coburn. The title of the book is Precalculus. This is lesson 5 in the second edition of the book. But as for the Philippine edition, this is lesson 1. So yeah. Exercises 1.1. Let's start with number 101. Please do know, please have your heads up, since I'll be making an entire video answering almost all of the questions in exercises 1.1. why won't I answer all the questions? Well, the answer is simple. I plan to focus on the more harder questions than just stay with the easy questions. The harder questions will be basically the word problems. Please, you can make recommendations for me to make another video about the easier ones. But for now, I'll be focusing on the hard ones. Anyways, for number 101, winch drum. So that's the theme of this word problem. The radius is 3 inches and it turns at 20 revolutions per minute. So we have to find the angular velocity. So specifically, we're supposed to find it in radians. That won't be a problem since, if I'm not mistaken, usually our answer for W is always in radians. It would be another step harder if we're tasked to find the angular velocity in degrees. So yeah, let's apply our current knowledge. So W, or angular velocity, is equivalent to 20 times revolution. Then our time is minute, so 1 minute. I think that's standard. Every time the time will always be 1 minute. Every time the given is always RPM, or revs, or revolutions per minute. So let's further progress. 20 times 2 pi over 1 min, which is 40 pi over 1 minute. So 40 pi, this is the angular velocity. Yeah, this is the angular velocity. I should fix my number 1. It's so ugly. That's better. Okay, for letter B, we have to find the linear velocity in feet per second. So I've already laid out here the conversion values. So 1 feet is equivalent to 12 inches. I hope that's already familiar with you. 1 minute to seconds, that's already pretty obvious. I think this is one of the most easiest conversion factors to memorize. So to find the linear velocity in feet per second, so V, it should be in black color. Anyways, V is equal to radius. Our radius is 3 inches, so 3 inches times our W, which is the angular velocity, which is this one. So it's 40 pi over 1 minute. I'm so sorry. I forgot to put rad again. There you go. This is the final answer for angular velocity. Pardon me. So we have something like this. By the way, for radius, I also forgot. I'm actually not used to it even to this day. 3 inches. Every radius will have a per 1 rad as its denominator. So yeah, basically cancel those two units. So currently we have inches per minute. As you can see here, we want it in feet per second. So let's first start with eliminating inches to feet. So inches here. Inches should be in the denominator. And our new value, which is in feet, should be at the top. So 1 feet is 12 inches. Cancel the units. Simplify, this is 4. But we don't really have to cancel, cross cancel if you're going to put the values after we compile them in the scientific calculator. So for minutes to seconds, so 1 minute is 60 seconds. So we cancel the minutes. Put all of these values in the scientific calculator now. We have clearance. We get 1/6 pi feet per second, or 0.52 feet per second. This is the final answer. Alright, let's move on to letter C. We have so much space. Let's put it here. So, the question now is, how long will it take to get the load to the height of 60 or never mind, 6 feet? So we apply this kind of triangle in this word problem. I know it came out of the blue. The lesson never really involved the use of this triangle, velocity, distance, time, or in other words, how I coin it as the VDT triangle, or velocity, distance, and time. How long will it take to get a load to the height of 6 feet? Why do I keep saying 60? Anyways, so the question here is time. What's missing is the time, and based on this triangle, time is equal to distance over velocity. This velocity refers to the linear velocity, the value which we found earlier, which is this one. So v, as we know it, is equal to 0.52 feet per second. Time will always be in seconds, and distance is, of course, obviously in feet, as summarized by the velocity. So we do have data about what distance is. It's 6 feet based on this word problem. So d is 6 feet based on the given, not word problem. T is equal to 6 feet over 0.52 feet per second, or basically 6 over 0.52. That would get us 11.5 seconds. It takes us 11.5 seconds for the machine, how do I say this? The winch drum machine to get the load, the current load to the height of 6 feet. 11.5 seconds. Right. We have another word problem here and another. So we have 2 word problems left. Let's finish them as early as possible. The park's roundabout. Anyways, I did understand the context at the first place. This is in a park. The roundabout. It's similar to a carousel. In certain aspects, but I think you get the image or the picture. The radius is 56 inches and the turn is 3/4 revolutions per second. So right now it's RPS, not RPM. What difference does it make? For finding the angular velocity, this is how we write it. So 3/4, then revolution. You still write the numerator as is, regardless of what number or coefficient is in whatever form, in fraction or in decimal, or in just as a whole integer. We still put it in the denominator multiplied to revolution. Time, this time because it's RPS, this time it's per second, per every 1 sec. So 3/4 times 2 pi over 1 sec. We get so 6/4, 3/2, 3/2, or in other words 1.5 pi rad over 1 second. This is the angular velocity. I'm so glad I remember that we're supposed to put rad beside theta in the numerator of the angular velocity fraction. So now that we know the value of angular velocity, we could now proceed to finding the value of the linear velocity. So as you can see here, I've plotted in the values of the conversion factors that we'll be needing later. You might be wondering why I wrote 1 mile in inches conversion factor this way. I was practicing earlier. I wrote different numbers, so it's supposed to be 5,280, which is in other words, again, 63360 inches. Okay, so velocity is equal to radius. Our radius is 56 inches. And our W, which is the angular velocity. By the way, before we proceed to writing the angular velocity, or W, 56 inches, we put as denominator for the radius. For every radius is 1 rad per radians, or per 1 radian. So yeah, let's move on to writing the W. So it's 1.5 theta rad over 1 second. So currently our given is in the unit inches per second. We want it in miles per hour. I didn't know I wrote this earlier. I was supposed to remove this. Anyways, so from inches to miles, 1 inch, actually no, 1 mile is equal to 6,360 inches. So we eliminate inches unit and we bring in the mile. As for the time, seconds, so 1 hour is equal to 60 minutes, which is also equal to 3,600 seconds. So 1 second, I'm sorry, 3,600 seconds is equal to 1 hour. Okay, and so let's cancel the current units that we have and bring in the new ones. So now we have mile per hour, or mph. Put all these values in the scientific calculator and we get 14.99, or approximately 15 miles per hour. So yeah, that's it. This is our linear velocity. So let's move on to practice question number 97. The area of a sector. This is an application of our formula area of the sector, but the two formulas that I introduced to you earlier. So a water sprinkler shoots water at a distance of 12 meters. So distance, any distance whatsoever, will always be the radius. You don't have to doubt about it anymore. I screwed up an exam about this the first in our first take, because I didn't know that whatever value that involves meters in the given that's not area is obviously the radius already. That's something that I didn't know. So actually eventually realized that I couldn't solve it, but initially I could if I already knew at the time that any value that involves meters is already the radius. So don't repeat the same mistake as me. Anyways, rotate. It rotates to an angle of 40 degrees. Theta is 40 degrees. We should express it in radians. So it's 0.698 rad. So area, this is the formula that we'll be using, since in letter A, we're looking for the area of the lawn it waters. So A is equal to 1/2 times the radius, which is 12 meters squared. Then our theta, expressed in radians, is 0.698 rad. Let me make something clear. Let's go back to the formulas above here. So for this specific formula, whenever we want to find A, theta should always be expressed in radians. But for this formula, the one with 360, just to make it easier to remember, theta is always expressed, this is by the way, or they can't be missing at the same time. Otherwise, I don't know, we couldn't really apply literal equations here. Anyways, theta is always expressed in degrees. On phenomenal occurrences wherein theta is expressed in radians in this formula, I just don't know about that. I haven't seen possibilities or proofs that that claim has been proven, if that makes sense. Anyways, I hope you get the point. In this formula, theta is expressed in radians. In this formula, theta is always expressed in degrees. Period. Alright, let's go back to letter B. Actually, no, letter A. We haven't finished it yet. So, 1/2 times 12 raised to 2 times 0.69813170008. I just simplified it to 0.698. It's basically 50.27 meter squared. This is the final answer. Okay, so in letter B, the radius is still 12 meters. The angle, or the theta, is missing. And given that the area is twice, as stated here, so A is equal to 50.27. This is the initial value. Then we make it twice, so times 2. A is equal to 100.53 meter squared, particularly for this situation. So 100.53 meter squared is equal to theta, which is missing, over 360 degrees times pi times 12 meter raised to 2. We multiply both sides with 360. To cancel what we have here, and you have 36,191.14737. This is the product of these two values multiplied to each other. And at the other side, we have 12m raised to 2 times pi times theta. We divide both sides with what we have here at the right side. Divide both sides just like this. So we cancel, so that we could leave theta alone at one side of the equation. And here, put those values in the calculator, we get 80 degrees. This is the final answer. If the question doesn't actually require you to express theta in a specific unit, either radians or degrees, then you could just leave the answer as is in its initial value of degrees, since, as I said earlier, this formula will always assume that theta is expressed in degrees, not radians. Okay, so let's solve for letter C. So theta is 40 degrees, range is missing, and still our given is the area is still the same, twice the initial value. So sorry. This is the last question. Let's give it a shot. I'm sorry, I just need my calculator for a moment. My iPad died. The answer key cannot be seen anymore. Okay, I'm back. I'm sorry for taking it for the inconvenience. Anyways, for A, it's 100.53 m raised to 2. Then at the other side, it's theta over 360 degrees. Theta, such that theta is 40 degrees. So 40 over 360 times pi times the range. Range, by the way, is another way of saying radius. So yeah, just so you know, to avoid the possible confusion. So the same drill, the same thing that we usually do, 360 cancel out each other, and for The other side, 360 times 100.53, it is 36,190.8 meters squared. And at the other side, it's 40 times pi times radius raised to 2. And we divide both sides with 40 pi. So we have r raised to 2. And on the other side, put this value in the scientific calculator. So 36,190.8 over 40 pi is 287.9972357. So put a square root sign on both sides, and we get, sorry, this is going to be quite long. So square root of 287.9972357. Our answer is 16.9704813. But then, if we round it off to two significant figures, our answer is basically this one. Oops. This is the radius. There we go. Okay, I think this video is finished. I'm very sure that these are the final answers. These answers are correct. Even so, just in case you have the actual pre-calc book authored by John Coburn, you can always check the answers at the back of the book. So yeah, this is everything. I hope this video helped you a lot, or quite in a certain extent. I do also have my limits, but I can assure that I did my best to teach you the essentials, what you're supposed to know for this specific lesson in regards to degrees, radians, conversion factors, and angular and linear velocity. I'll see you in the next video for more practice questions. Thank you for watching.